and run with it. So I wasn't going to go down this path, but since Gregg already started there,
I have
he
to.
opened up the doorway and kicked me right
Yep.
through it. So I'm going to give you two scenarios. One is this is why you shouldn't use this meter. And I'm going to give you a scenario that is why you should use this meter.
Yep.
Okay. So the first scenario, and I'm not picking on people. Some people, they do things and they don't always know.
On you.
In my past, when I was in the Army, we used this at one time when we had generators. And what the established doctrine was to go ahead and put a ground rod on each side of the generator and bond that ground rod to that generator. And yeah, we're going to have a couple other generators in parallel, but then you're going to go up to each of the ground rods and you're going to put this side on there. You're going to clamp it. You're going to say, hey, it's less than 15. Cool. Move on. Next one, they should all be less than 15. Well, guess what? Every single one on each generator, for both of them, were the same number. Well, why? Mm-hmm. Because exactly what Gregg just said. This is a loop check. Yep. So it's injecting through the earth down, comes out the other ground rod, comes back up to this ground rod. It's only checking itself. The only way that this really works well is when I have like 18 ground rods, right? Mm-hmm. And so then it goes down one ground rod, it goes through the earth and comes back through all 18 as a parallel path. And then all of them, because they're in parallel, they basically reduce down to a parallel resistance, which is very low. And, that they all might be 15 each, but 18 or 15 divided by 18 is less than 1. So now we got 15 ohms on this one rod plus the 0.6 ohms. Well, now you're actually getting something more comparable to what the ground rod really is. So they were just doing two rods, and that's the wrong scenario for it. So that's why I personally, every time someone pulls one of these bad boys out, I cringe. I cringe so bad because it gives me horror stories from when I was in the Army. So that's now the second one is great use for it, right? So utilities like to use these commonly, and they'll go up to a telephone pole and they'll have a grounding rod come down or conductor, and they'll go ahead and that goes up to their shield wire at the top, right? Mm-hmm. Bonds to their shield wire or neutral. They'll go up and they'll measure the one rod. The thing is it goes in the earth and it comes back up 100 other rods back up to those shields, like I was saying before. And now we're only really checking one rod. All the rest of them have an infinite parallel path. And so at that point, perfectly acceptable, right? So you have to, it's like any test, right? If I use a multimeter and I want to go measure how much current's coming out of my battery, I'm not going to set this to amps and go right across positive and negative, right? You have to know how to use the test before you employ it.
Mm-hmm. Yep. Yeah. And that's probably the chief issue that we hear about this instrument. When we look at our tech support calls, it's usually how do I apply it, or I'm producing this value. What does this mean? Your ground electrodes don't have, most likely, a quarter of an ohm of resistance to ground. Most likely. I mean, there are scenarios that will be the case, of course, where we have, like Tom mentioned, we have 18 ground electrodes in the ground, or we have a very, very low resistivity soil. However, generally speaking, I can safely assume that I don't have a quarter of an ohm resistance on a single electrode. We hear though, hey, I got this measurement. This instrument in particular will produce a loop alarm, and that is not a magic loop detection. It's simply saying you have a resistance threshold of 5 ohms or less. You've met that threshold. You could potentially be connected to a loop. For instance, in a cabinet that has a bare ground electrode conductor that is somehow making contact with that cabinet in two locations, has developed a loop now, and I've clamped onto it, and I'm just seeing that test current return over and over and over again. We're going to consider how the instrument works, and then we can apply it correctly. I think the best way to simplify it is to remember that it's a loop impedance analyzer, and think about the path of least resistance, where that's going to be. That's where your test current is originating. It's where it's headed, and it's returning back through the earth if it's a resistance to ground test. You are incurring a very low resistance connection through the utility's neutral, because it is essentially, for all intents and purposes, infinite. And so therefore we are measuring that test current return into our ground electrode. Two reasons this instrument's going to produce a slightly different value than our follow potential. The first one is the fact that we do have some resistances incurred behind the electrode that is being measured, right? As Tom mentioned, zero point 0.6 ohms, for instance. So if my fall potential measurement was 12 ohms and this was 12.6 ohms, well, that 12.6 ohm is incurred because of the utility system. Secondly, frequency. We all remember way back in school that impedance is a function of frequency, and as its frequency increases, therefore so can impedance. So we've got ground systems are very complex. They have capacitive and inductive components on them. Oftentimes, usually for our purposes, we can somewhat move those to the side. However, in this case, because I'm increasing the frequency that I test at, here I'm testing at usually 128 hertz. Here I'm testing at 2078 hertz. I expect to have some type of inductive property, perhaps, that is going to change the measurement, the impedance measurement on this instrument. So there's two reasons that we could see this instrument be slightly different. However, all things considered, I've done this many, many times to demonstrate this and do training on it. I should see very, very similar measurements on these methods when done correctly. We should mention that fall potential requires isolation, because if I have that looping condition there, I now have a bunch of parallel pathways for that test current to return back into the instrument. I'm going to see very, very low resistance measurement. That is not a true measurement of the ground electrode I'm connecting to. So for fall of potential, now there are ways to move around this that we could talk about, but for a fall of potential where I do not have a current clamp or other type of test method to apply to it, I have to isolate, which means I should be de-energizing in most cases.